So we've introduced the electric field, and so now we're going to discuss how to visualize the electric field. So just a reminder, the electric field is an abstract mathematical way to represent how source charges distort space. And then it's this distortion that influences our test charges in our problems. So the big question is, how do we visualize the electric field? Well, the electric field is a vector, so one way we can visualize the electric field is with arrows. And so I've got this figure on the left here where we've got plotted a bunch of electric field vectors due to a point charge. And so if you remember back to the video on the electric field vectors will point away from a positive charge or towards a negative charge. And so what that means is that here in the center, we must have a positive charge because those field vectors are pointing away from that center point. And you'll notice that if we zoom in here, you'll notice that the vectors are large, really close to the charge, and they're getting smaller and smaller as you move further away. And in fact, they're getting smaller, like 1 over r squared. And the vectors that are drawn here are just drawn in sort of regular intervals, but the field exists everywhere. The field exists here, the field exists here, the field exists over here. This is just a way to represent the distortion that this positive point charge has created. Over here we have pretty much the same picture. We have now a 3D representation because the previous was just a 2D projection. But again, we must have a positive charge here in the center because all of those electric field vectors are pointing away from that point. Okay, so electric field is a vector. We can determine the size of this vector from E is kq over r squared. That would be the magnitude, and then of course the direction is pointing away from the positive charge. Of course, if this was a negative charge, those vectors would be pointing towards the negative charge. So down here at the bottom, I've got another figure from the book. And this figure now shows a slightly more complicated set of electric field vectors. And so from this picture, we should be able to realize that there must be 2 charges in this picture. Over here, there must be a positive charge because the vectors over here on the left are pointing away from that location. And then over here on the right-hand side, there must be a negative charge because the vectors over on this side are all pointing towards that charge. All right, so again, you've got 2 point charges. So if you wanted to calculate the electric field at this spot right here, what you would do is you would take you would calculate the contribution from the positive charge, and that might be pointing that way. And you'd also calculate the contribution from the negative charge, and that might be pointing this way. And when you add those 2 vectors together, you'll get a vector that looks something like that. All right, so that's how each of these vectors that are sketched out, the size and the direction, all of those are determined by adding the 2 contributions together. Remember, for a point charge, the magnitude of the electric field would be kq over r squared. Right, so you'd have to do that twice, once for the positive charge and once for the negative charge. And so what I want to point out is that we can use these vectors to represent the electric field, where the length of the arrow is the magnitude and the direction of the arrow is the direction of the electric field. But we can also do another thing, and the easiest way to see that is by me sketching out some of these. So if you draw lines that start at the positive charge or surface and terminate at the negative charge or surface, then you can begin to sketch out what are known as electric field lines. And this is an alternative way to visualize or represent the electric field produced by source charges. All right, so now we're going to talk about electric. All right, so electric field lines demonstrated here. So on the left, I've got a positive point charge, and rather than drawing individual vectors, I've drawn electric field lines. And so again, the lines originate at positive charges. They would terminate at a negative charge, but in this figure on the left, there's only a positive charge in the space. And so the electric field lines are drawn as such. And so over on the right, I've got two charges. This is known as a dipole. And the electric field lines are sketched out there. Again, very similar to the electric field vectors, but this is sometimes a more useful way to visualize the electric field. Now, when you had electric field vectors, the strength of the electric field was determined by the length of the arrow, but there are no individual arrows now with electric field lines, and so the electric field strength is represented by the density of the electric field lines. So if you look over here in this image, here the 7 electric field lines that I've got drawn are going through a smaller area than over here. And so the field is stronger versus weaker in these two locations. So when you're looking at a diagram, the density of the lines tells you immediately where the field is strong compared to where it might be weak. I mentioned this already, but the electric field lines originate at a positive charge or surface and terminate at the negative charge or surface. This is an important one. Field lines never cross. And if we have conductors in a problem, then the field lines originate or terminate on the surface at right angles at 90 degrees. And down here, there's just 3 more examples of electric field lines for different charge distributions. So over here on the left, this is known as a dipole, where the positive and negative charge have the same magnitude. This is a setup where you have 2 positive charges, 2 like charges, and so the field lines look different. And then over here on the right, you've got a positive and a negative charge, but this isn't a dipole because the positive and negative charge are different amounts, they're different magnitudes. Okay, so the last thing that we want to talk about, actually in this chapter, is the electric dipole. So a dipole is the term that we use for when there's a positive and a negative charge. The amount of charge is equal. So in this case, I've sketched a dipole where the charge is the amount Q. And the way that we describe the dipole is that we set the separation as the distance d. This separation vector points from the negative charge towards the positive charge. And when dealing with a dipole, you can define the dipole moment as this vector quantity, which essentially is a combination of the charge of the dipole with the direction or the orientation. So the dipole moment is defined as q times the separation vector between the two charges. And again, the vector d points from the negative charge to the positive charge. So something interesting happens to a dipole when placed in an electric field. In this picture here from the book highlights what's going on. So let's take a look at this. So I've got my, we'll focus over here on the right, the same picture. I've got my negative charge, my positive charge, and my dipole moment vector pointing from the negative charge to the positive charge. And this dipole is in an electric field, and so the negative charge is experiencing a force to the left, and the positive charge is experiencing a force to the right. Now, both charges are in the same electric field, and they're both the same amount of charge, and so the magnitude of those forces is exactly the same, and so the net force on the dipole is actually 0. But the net torque on the dipole is not 0. And in fact, if we do a calculation for the net torque choosing the center of the dipole as the place we're going to measure the torque about, we end up figuring out that the net torque is equal to QD cross E, or substituting the dipole moment, the net torque is the dipole moment crossed, or the cross product, with the electric field. So that's wonderful, but what does it mean physically? Well, what this means is that dipoles placed in an electric field will align with the field. So that means the dipole will rotate if it's not already aligned, and it rotates because of that net torque. The last thing we're going to mention is that it's possible for things like atoms, when they're placed in an electric field, to have dipole properties, and that's because placed in an electric field, the atom there can be an induced dipole, and so that's what we've got pictured over here on the right. Oops. Place this atom in an electric field, all of a sudden positive charge is separated or is moved a little bit off center, so the positive charge is a little right of center, the negative charge is a little left of center, and so you end up with a dipole moment pointing to the right in this atom. And that is all of the things that we want to talk about for this chapter 5.